Hey folks, going through another momentum example for you. This is number 16 in your textbook. So, picture on the left is what the system looks like before the impact. This object here is moving to the right here at 5 meters per second. Object B moving left at 2 meters per second. They impact in a head-on collision here. After the impact, both objects, I would presume, would be moving to the right after the impact. Now, again, with these velocity vectors, sometimes you can tell, sometimes not. If you can't tell a direction, you just take a guess at it. And it's no problem as long as you're consistent writing all the equations. If you actually have the direction wrong, you'll just get a minus sign in the answer. But here it's pretty, I think, reasonably evident what's going to happen, because mass A's momentum is 2 times 5, 10 kilogram meter per second. Mass B's momentum here in picture 1 is 4 times 2, 8 kilogram meter per second. So the net momentum of the system is to the right. Now that doesn't actually guarantee both of these will be moving right. It's completely possible that you can have a system where the net momentum can be going to the right, but have one moving left after the impact, but that's not going to be the case. I don't believe that'll be the case here. But anyway, moving on. So we can write a momentum conservation equation for this. So conservation of momentum. Go ahead and just call it right positive. And we're going to have MAVA1 minus MBVB1 is going to equal, over here on the right, MAVA2 plus MBVB2. Right? Now, this has two unknowns. We don't know VA2, we don't know VB2. However, we also know that the coefficient of restitution for this problem is 0.4. So 0.4 is going to equal VB2 minus VA2 over VA1 plus VB1. Now at this point you may be saying, this is supposed to be a minus sign between them. Well, when we went through and derived that expression for coefficient restitution, if you actually look at it in your notes, we had both objects moving to the right before and after. And the reason for setting it up that way is just it makes it very easy for plus and minus signs now. So now what we do is I'm calling right positive. So VA1 minus VB1, keep in mind that VB1 is to the left, so effectively it's minus a minus, making that a plus. This is now just a magnitude in this equation here. So if we go ahead and put numbers into this, this is now going to read 0.4 is equal to VB2 minus VA2 over 7. 7 meters per second. And now what we have is a pair of equations, two unknowns. So if we go ahead and solve this system here, equation 1, equation 2, and solve this for VA2 and VB2, when I do that, I get that VA2 is equal to minus 1.53 meter per second, and VB2 comes out to be, can't read my own writing here, I think that's 1.27 meter per second. I'm going to take a moment and just check that. Okay, so yeah, I went through and double checked that calculation. I believe that's correct. So alright, going back to kind of interpreting our results here. So VB2 came out to be positive 1.27 meter per second. You'll notice VA2 came out to be minus 1.53 meter per second. In my original work here, I assumed that VA2 was to the right, but I assumed wrong. Now, there's no problem with that. What we know now is that VA2 is 1.53 meter per second to the left. Or we can just put opposite direction shown, either one. So again, there's absolutely no problem with guessing a direction on a velocity vector, even if you guess wrong. In this case I did, and you still end up with the right answer. So hope that this helps, and I'll start working on another one.